What element flows like water, outshines like silver, and slowly poisons everything it touches? The answer is quicksilver, a name that captures its fleeting, lively nature. We know it today as mercury. It is a substance of deep contradictions, a metal that refuses to behave like one. It is the only common metal that remains a liquid at room temperature, a trait that has fascinated and bewildered people for thousands of years. You could hold a pool of it in your palm, feeling its surprising weight as it shimmies and rolls like a living thing. Its surface gleams with a perfect mirror-like finish, reflecting the world back in distorted, silvery shapes. This unique combination of properties made it seem magical, a substance caught between the solid world of earth and the flowing world of water. For centuries, this beauty was an irresistible lure. Humans saw its strangeness and ascribed to it incredible powers. Some believed it held the key to eternal life, a divine elixir that could cheat death itself. Others used its reflective sheen for cosmetic purposes, hoping to capture a fraction of its otherworldly glow. Alchemists, the mystics of early science, considered it one of the three prime substances from which all metals were formed. They saw its ability to dissolve other metals, like gold, as a sign of its fundamental power over the material world. It was an element of dreams, a physical embodiment of transformation and possibility. But this long love affair was built on a terrible misunderstanding. The very thing that made mercury so captivating was also the source of its insidious danger. Imagine a single perfect drop of mercury resting on a dark wooden table. It pulls itself into a tight spherical bead, a tiny, heavy world of its own. If you were to nudge it, it would not smear or wet the surface. Instead, it would glide away, maintaining its perfect form, before perhaps splitting into a constellation of smaller, identical moons, each one a perfect copy, rolling with an eerie, frictionless grace. Why does mercury, a heavy metal, behave more like water than like its metallic cousins, iron or gold? The secret lies deep within its atoms, in a strange and subtle dance of subatomic particles. In most metals, loosely held outer electrons wander and mingle, forming a strong metallic bond that locks atoms into a rigid lattice. That is why a bar of iron is hard and strong. Mercury plays by different rules. Its atoms are exceptionally heavy, packed with 80 protons. Relativistic effects pull inner electrons inward and tighten them, shielding and holding outer electrons unusually close to their own atoms. Those outer electrons become reluctant to share, antisocial dancers in a room full of atoms that want to join hands. Without strong bonds, atoms slide past one another. That fluid motion is what we perceive as a liquid. Only at about -38 Celsius does mercury freeze into a crystal. This aloofness explains its perfect beating, and why atoms can evaporate as invisible, odorless vapor even at room temperature. Long after the alchemist's dreams faded, mercury found a new role as an indispensable tool of science and industry. Its predictable behavior made it the star of measuring devices for centuries. The most familiar is the mercury thermometer. As temperature rises, the liquid expands linearly, pushing a silver column up a graded scale. When it gets colder, the mercury contracts just as predictably. This principle also powers the mercury barometer, invented by Evangelista Torricelli to measure atmospheric pressure. A column rises and falls as air's weight changes. A falling glass often foretold a storm. For sailors and scientists, it was a crucial window into invisible forces. Beyond measurement, mercury's conductivity made it key in electricity. In tilt switches, a drop of mercury flowed to connect contacts. On one tilt, it completes a circuit. On another, it breaks it. Durable and spark-free, these switches served thermostats, appliances, and industrial controls. Fluorescent lighting relied on a tiny amount of mercury vapor. An electric current excites mercury atoms to emit UV, which strikes phosphor to produce visible light, far more efficient than incandescent bulbs. From telling temperature to lighting rooms, mercury became a quiet, shining servant woven into daily life. It's complicated. The danger of mercury lies in its subtlety, its ability to enter the body unnoticed and inflict damage slowly over time. While swallowing a drop of liquid mercury is surprisingly less harmful, inhaling its vapor is a different story entirely. Heated mercury evaporates into an odorless gas that can be breathed without notice. Absorbed in the lungs, it enters the blood, crosses the blood-brain barrier, and targets the central nervous system. It disrupts cellular processes, damages cell structures, and interferes with chemical messengers. This damage is cumulative. First signs of chronic poisoning, often called Mad Hatter disease, are subtle. Uncontrollable tremors and shaking, particularly in the hands. Irritability, shyness, sudden mood swings. Memory begins to fail. Concentration becomes difficult. Speech may become slurred. Coordination deteriorates, making simple movements clumsy. In severe cases, hallucinations, delirium, a loss of cognitive function. The poison works silently, dismantling the very organ that defines who we are. Acute high-dose exposure can scar lungs, damage kidneys, and kill, but the slow poisoning has been most insidious. Mercury's danger is magnified by its ability to travel vast distances and transform into a more potent poison. It often begins with burning coal. Trace mercury is lofted high by smokestacks. Other processes add more. Winds carry it across continents until rain, snow, or fog brings it down to lakes, rivers, and oceans. In oxygen-poor sediments, bacteria convert inorganic mercury into methyl mercury, far more toxic and easily absorbed. It bioaccumulates from plankton to small fish, then biomagnifies up the food chain, leaving top predators with concentrations millions of times higher than the surrounding water. Thus, someone far from any plant can still ingest a potent neurotoxin on their plate. Despite what we know, mercury persists, especially in artisanal and small-scale gold mining across South America, Africa, and Asia. Miners mix mercury with ore. It binds to gold, forming an amalgam. Heating releases toxic vapor, often where families live and work. They breathe it in, the gold remains, the land and water pay the price. Meanwhile, legacy products, bulbs, instruments, fillings are tiny toxic time bombs. Improper disposal or incineration re-releases mercury into the air. Cleaning old contamination is slow and costly. Disturbing sediments can worsen things before they get better. The global community is acting through the Minamata Convention on Mercury, named for the city that suffered so grievously. Over 120 countries have signed on. The treaty tackles the full life cycle, bans new mercury mines, phases out existing ones, phases out mercury in batteries, switches, fluorescent lamps, cosmetics, and reduces industrial use and emissions. Targets small-scale mining with national plans, safer technologies, and community training. Still, implementation needs investment, technology, transfer, and political will. Even with action, mercury lingers. Its cycle is slow, and its poison moves through food webs for generations. The story of mercury is a cautionary tale of wonder and short-sightedness. For millennia, its liquid grace entranced us. We saw the shine, ignored the harm. Mercury once symbolized life, power, and transformation. Now we know it as a silent poison. How many other miracle materials are we still misunderstanding today? Yeah.